This?
Nice. Yeah.
Okay. All right.
We're good to go.
Okay. Good morning. Welcome everyone to day 2 of this meeting on galaxy mergers and the nuclei. And so we're starting the first session. We have 3 talks in the session. Each talk is 20 minutes. And our first speaker is going to be Dharam Lal, who's going to speak on identifying dual and binary active galaxies.
Good morning. I will be speaking about identifying dual and binary active galaxies. So the workshop had titled Galaxy Mergers and Their Nuclei. And I was debating what to speak about. And this is one of my favorite objects, over cluster. This is cluster merging with a small group environment. So every object or every galaxy that you see has been a victim of such a merger scenario. But then I just spoke 2 months back in the same room about these sources. I'll speak a little bit different, which was more than 10 years back, which I worked on. And this is a good opportunity for me to come back to this field. Probably I'm bored of Coma cluster for some time. Yeah, so I'll be speaking about dual and binary sources. What are dual galaxies and binary? Just to put the definition of these two classes of sources. Dual are essentially characterized by systems where separations are just several parsec or kiloparsec in size, whereas binary systems are essentially bound in the Keplerian system. So these are the two clear things. The one that binary essentially slope scales a system are bound by Keplerian system, and the other one are slightly larger than that. And you do want to hunt these sources because these are essentially important both to understand the galaxy merging scenario observationally as well as theoretically. And theoretically, if you want to do it, you want to understand hydrodynamic conditions of the gas surrounding mediums, etc. How galaxies assemble themselves, how major and minor mergers happen. We heard a little bit yesterday, including in a poster flash talk. I'm not a champion in this thing, so I will be using this opportunity to learn and understand this field. So if you have questions, we can discuss. I may not be able to answer. How do you go about doing this thing? You essentially look for candidate dual system, and then you want to pursue those candidates using different methods to make sure that these are either dual or binary system. So you essentially use survey fields, and Preeti talked about double peat class of sources, and chase those sources. Some turned out to be indeed these are dual binary systems. Some may not turn out to be so. Simulations have made little progress, but these are again difficult class exercise. So you do competing best simulations are Magneticum and Horizon AGN. And it heard right in the back. Yeah. So typically what input parameters that go into simulations are you essentially put black hole mass ratio. So since you can typically choose both are of same mass because you want dual AGN by definition. And they also put in a probability fraction that closer the system, the more likely you will be having a dual active galaxy systems. And what are predictions of these simulations? The AGN horizon has made good predictions. See, it is G of 2 where the AGN population peaks and where the population peaks. These are typically so fraction of dual AGNs for the total number of sources, and for all sources which are galaxies mass greater than 10 power 10 solar masses, the fraction is just 2%. If you increase to 11%, 10 power 11 solar mass, the fraction increases to 11% or so. Whereas on the other hand, Magneticum, if you do it, the number reduces by almost 1 order, 0.2 for sources which are greater than 10 power 10 solar masses, and just 1.7 or 2% for galaxies which have masses more than 10 power 11 solar masses. The two, if you compare the two systems, essentially the difficulty is how do you reproduce observed properties of AGN as a function of redshift? That's one thing. Another is how do you define these dual. So in one case, you're defining dual AGN where separation between the two systems is less than 30 kiloparsec. In another case, you have kept that free parameter, and then you define this. Having said this, bottom line is the following: that some level of dual AGN activity is seen as soon as you have galaxy merger. although the opposite is not true always. Okay, observationally, there are variety of things to do. You can look at morphological signatures, you can look at spectral signatures or periodic variation of the light curves. And I've listed some of them. I'm not going to talk about all of them. Things which I understand, which I've used, which I understand more, is what I'll be talking about over here. First example is dual systems where you have essentially dual core. This was first, and that is where the dual agent field essentially moved heavily. So this is Chandra. So what the image which you are seeing is pointers.
The pointer is still in that room.
Okay, no worries. So what you see over here is essentially a pair of AGN systems. So the blue color which you see is Chandra image, as well as the other red color image is also Chandra. Red is in soft band of Chandra, which gives you very fantastic angular resolution. And blue is clearly showing that there's two nuclei clearly detected. They're separated by distance of a kiloparsec or so. This was an X-ray. In radio, there are two examples. For example, the left one is 3C75, where you have classic two AGNs which are in close vicinity. They are separated by 8 kiloparsec or so. The next example is using millisecond scale imaging of a radio galaxy. What you see, the two C1 and C2 over there are two cores which are very near in the near vicinity of the order of 7 parsec or so, and both are flat spectrum features. Only one of them has an optical counterpart. The next has not been seen, but the probability of finding two closely spaced to this distance along the line of sight, even if you assume the other is far, they are not dual systems, that probability is extremely small. So based on that, they make a conclusion that the authors particularly that these are binary systems. And the third one is another example in radio, where in NGC 7476, I think, the core was found to be consisting of two C1 and C2 split into two, and these are at a distance of less than a parsec. Right. You can also use jet vehicles or helicity. Essentially, what happens if you have two merging systems? One of the jet is essentially active galaxy, and you will, because it is a two merging system, this accretion disk is going to play around, and this is going to create helicity or wiggles in the jet on millisecond scale. So that is another example which people try to look at. Yet another example is X-shaped sources. I'll come to these once again, where we think that a jet which is moving out has essentially got shifted from one location to the other location. Yesterday, Preeti talked about double peak or asymmetric features seen in optical narrow line emissions. So you clearly see there are two double peaked narrow line emissions in the spectra, and this each peak correspond to two nuclei in the system. Having said this is not always. There are false positives also. What you see in the bottom is spectrally identical feature, but the actual thing is one AGN where you have extended narrow line emission seen over there. You can also see periodic light variations in active galaxies. Example is OJ 287. What I have again the same. These are two merging systems. Because of the merging, the disk of one is wobbling around, and because this system has also active jet. Now jet can point along my line of sight or away from the line of sight, depending on its pointing towards the line of sight. The emission get Doppler boosted, hence you see periodic light curves. And what you see over there are essentially light curves seen in different bands. So these are another signatures. Good. So I'll shift to one of these class of sources, which is what I have worked on once. I want to take this once again. So this 3G 2 to 3.1 was first source, which was observed by Top and collaborators. And you see two images, 1.4 gigahertz and 8.4 gigahertz, nearly at identical angular resolution. And you clearly see a pair of active lobes, the north-south, and then the perpendicular, really perpendicular to it is very diffuse low surface brightness, another axis. So I'll come to the formation scenario. So these are thought to be that these are probably the merging systems where you essentially have one axis got tilted to another axis for two independent things. Additionally, what you see is small ticks, which are like talking about the polarization properties of these sources. And if you look at polarization properties at 1.4 and 8.4 gigahertz, and this bottom left panel is essentially asking a question that is the polarization tick shifted from 1.4 to 8.4? No, so it has not. That shift is what is plotted over there. The narrow peak essentially tells that the shift is very insignificant in the sense that magnetic field structure hasn't changed across two observed frequencies. So these are very robust observational results. Now, how did this come into picture? You can say that one jet essentially was moving in this direction, the thing stalled over there, and then there was a backflow in the other direction that created the wing-like feature in the perpendicular direction. So the problem here is either then jet has to be strong enough so that it stalls at the hotspot locations or the active loop locations, and then it moves further. Thank you. So it comes over there, and then it further can move over here. Another feature is you have a jet, which is essentially precessing. So you are moving from one location to another. If you have this orientation, then there should be structures linking from 1 to 3 continuous structure kind of things. You can improve this model, say that you add a one axis and then it suddenly switch to another axis, and but jet was active. Now, once you move from 1 to location 3, then at location of 2, I should see some signatures of the jet. Because of, and this can happen. Suppose that AGN is there in the vicinity, there is a minor dwarf galaxy. If the merger happens, the jet can flip from one axis to another. Now, because you don't see linking structures, you can say that from 1 to 3, I switch off the AGN, which is smart thing to do. That's another jet orientation model, but jet switched off from one location to another. Good. This is the only slide. I should thank yesterday's speakers, including Preeti, who gave a good presentation what are active galaxies, etc. This is Fenner of Rayleigh class 1 source, and this is Fenner of Rayleigh class 2 source. The only difference between these two is in one case you essentially have a termination of shock-like feature or hotspot. In another, you don't see. In this, the jet dissipates as it moves from core to outer regions. These are the sources which show backflow, meaning jet goes here, terminates, and then you see this is load surface brightness diffuse steep spectrum feature. So it's only FR2 radio galaxies which show backflow, largely because these are powerful radio galaxies compared to FR1 radio galaxy. And we'll be talking about these X-shaped sources, what happens here. Now, these FR1, FR2, which were known in mid-2000, were just dozen known sources. And all of them lie at FR1, FR2 peak, meaning they're not as powerful as FR2, neither these are as big as FR1. Now, is it sufficient to have jet emanating from this direction, reaching over here, and then you further make the plasma diffuse this? If you ask for time scale, that becomes a difficult over there. And because I don't see linking structures from here to here, that is another drawback. And in this, these are all at 240 megahertz, GMR 610 megahertz, DNA 1, but max angular resolution. I take any of the two pairs and divide to create spectral index map, which I put up over here. Then this high surface brightness regions are of steeper spectra compared to low surface brightness. Now I'm contradicting myself that in a backflow, it stalls at the hotspot, matter further diffuses, it becomes low surface brightness, which is spectrum. And active lobes are flat spectrum. Here it is the opposite. So we had dozen odd sources. We found equal distributions of wings to be steeper compared to lobes, active lobes, wings to be flatter compared to active lobes, and mix of the two. So we were lazy enough. We said, okay, these are two systems with fantastic two active galaxies, which are in binary systems. Now the problem is, how do I move next? So among dozen odd sources, this was a fantastic source, and there were three more where we had clear detection of nuclei. This is a 610 megahertz. This is a mass resolution of 610 megahertz. And this is 240 megahertz. You take these, divide to form spectral index map. This is flatter compared to the active lobe axis. So we asked a question, okay, can we do millisecond scale using of this? We tried multiple times. We failed to get observation from back. So And at that time, because Chandra observations were coming into picture, people were very strongly believing that interplay of radio galaxy and its environment is largely driven by hydrodynamic phenomena. So it was probably hard to push for us. So next step was we need to improve the statistics. What is it telling us? We picked up 16 more sources gleaned from first survey images which showed X-shaped structure. And we again repeated the same exercise. You observe it using GMRT at 240 megahertz, 16 megahertz, divide the two, ask what is happening along the wing axis and along the active axis, and look at the statistics. And that is what is shown over here. So this is a distribution where these are spectral index as a function of number of sources. If you are sitting over here, then wings have a flatter spectrum compared to active nodes. If you are on this side, you have the opposite. And this distribution is very symmetric. This tells me that the spectral properties of high surface brightness active lobes and the low surface brightness wings are more or less similar. There is no distinction over there. So we are again back to square one. And this was another friend of us who essentially took these X-shaped known sources in the literature and they put it up all together and they asked a question, okay, what is the distribution of hot gas environment? So what you see is radio contours put up on the X-ray images. Hot gas environment, what are they telling us? And lastly, because they strongly believe that they will not be able to push the paper, and it was strong conjecture that the morphology of radio source is governed by hydrodynamic phenomena. That is what they said, that things are most likely distributed along the minor axis of the hot gas distribution. Maybe it's easy to flow out. The same set of authors in the same year, this is the X shape, this has not come out well, this is the active axis. Here they contradict their own conjecture. This is the X-ray image, this is the radio image. What they say is, if you put optical, radio, and X-ray and look at the time scale for hydrodynamic phenomena, backflow phenomena, then it is contradicting that. Most likely these are merged and introduced reorientation phenomena. Good. So just to put the perspective, what I said, so you essentially discover these sources along these three methods. You have dual agent on the left side, you have binary systems. And what I gave example of some set of sources, they are sitting in between these two TGV, where things are at kiloparsec, things are completely bound versus over here. Today, there are like dozen black hole pairs in kiloparsec scales or smaller, and around 100 supermassive binary black hole system accessible. But in radio band, these are just handful. I give example of 3675, this little source over here, this C1, C2, and 7674, which I'm not showing here, and the X shift. This is a binary or not, we do not know yet. Now, to summarize, these are important because formation encompasses many scales, different environments. Searches is necessary. They haven't made much progress. Simulations are there, but these are called challenging, difficult. And having made, like, for example, in X-shaped sources, you have any spectral studies, you need multiple lines of evidence to say indeed a source is dual or binary system. Yeah, thank you all. Yeah.
Thank you, Dharam. Questions for Dharam?
So these exit sources, so do you find that the spectral index indicates that those outer X part, is that older than the inner part? I mean, does the spectral index separate those, the X part from the internal part?
Yes, and thanks. So if I take so question is the following: if I have X shape, I'm picking up edges at the edges. If I just move slightly inside, you see consistent result inside also. So if I go close to the core and repeat the exercise, pick up regions along this thing, then if it is flatter here, it is flatter here as well, and vice versa.
Oh, okay. So it's similar, you can't really.
I was just curious to know, like, how does this redshift evolution of these pairs because in interest of the JWST detecting very high, massive black hole in the early universe.
From radio, we don't have much information. These are still on the scale of 2 handfuls. The number of sources are very small. Simulations have pushed, and simulations are again concentrating more on redshift of 2 where the peak of aging population happens. They still do not know how this evolution happens. So it's an open ended. If somebody wants to take it up, it's a fantastic project to look at. Sorry.
An amazing talk. So, you have shown two pictures of FR1 and FR2 galaxies, right? Where the hotspot of FR1 galaxy is near the core, and for the FR2 it's outside. So, is there any chance that an FR1 will evolve into an FR2?
Oh, okay. So first correction, if I made a left you with a wrong information. FR1s do not have hotspot. The jet dissipates as it moves towards the outer limits. And here, FR2 sources, you clearly see hotspot. Now, your question from transitioning from this to this is still a question mark. Why? Because in the nearby universe, bulk of these sources are seen in group or cluster environments, whereas all these sources are field radio sources except this little source over here, which is in a cluster environment. Now, if you go to slightly higher redshift, then things start to mix. You see FR1s, FR2s, as well as FR1s in the hot gas environment, but that statistics is very poor. So we do not know the answer.
Thank you.
So I think in the interest of time, I'm going to just use this opportunity to ask you one question. In one of your slides, that one with the your source, maybe ahead.
My source.
Yeah, this one. So the top left corner, are there two cores?
No, wait. So
Huh?
this is just, no, there is no two radio core over there.
Like
This guy is not detected in 240 megahertz at all. It's
Huh.
only over here, and we probably believe this is just a background or something.
Okay, we will show it the background. Okay, perfect.
Nothing.
Okay, on that note, and maybe we can discuss over tea. Let's thank Dharam and we will move on to the next speaker. That is Smitha Subramanian, who's going to talk about low mass galaxy encounters star formation.
So, good morning, everyone. Thanks to Moshmi and Sudhanshu for organizing this nice workshop. And today I'll be talking about galaxy encounters and star formation, mainly in the context of low mass galaxies. So, we know that galaxies come in different flavors, from giant ellipticals to dwarf irregulars. And there is one of the main interesting questions in the field of galaxy evolution is how galaxies evolve. There are multiple processes, which is on the right. You can see that like there are many of these processes are outlined here. This is the image taken from this paper. So on the top are the fast processes, and on the bottom are the slow processes, and the one on the left are the internal processes, and the one on the right are the external processes. So in the early universe, it was mainly dominated by the mergers and fast processes. Now we are moving into a secularly evolving, slow evolving universe. So now when I say internal and external processes, like external processes are mainly mergers, minor mergers, and ramp pressure stripping, etc. In terms of internal processes, there are bar instabilities, stellar feedback, and all those. So all this can affect star formation and other evolution of galaxies. So mainly our work, a group works on these processes, the effect of the influence of external and internal processes on galaxy properties, such as star formation, morphology, structure, etc. So in the context of this meeting, I'll discuss the effect of low mass galaxy interactions on star formation properties. So before going to the low mass galaxies, what do we know about massive galaxy interaction? When I say massive and low massive is like in this context is more than 10 to the 10 solar mass, the stellar mass of the galaxy, and anything below that can be considered as low mass galaxy. So what do we know? Like we know that these massive galaxy interactions can affect morphology. It can it can create tidal features around these galaxies like this, and also this is an interacting system, and also it can change the morphology from a spiral to a spheroid, and it can, in the plot in the middle, shows the enhancement in star formation rate when, like, okay, so yesterday we had a discussion, like if galaxies can come closer to it, so it will be just in a pair, and when it actually merges, it's a complete merger, and then the phase after that is the post merger phase. So when, like, as a function of pair separation, the enhancement increases, and it is maximum when it is in the merger state, and then it falls down in the post merger state. So the same thing you see in the AGN effect also. There is an excess of AGN and starburst in the when in the interacting systems, and then it peaks in the merger state, and then it falls down. So this kind of the studies based on, so these are some recent papers. So many of these are, like, there are a lot of papers in this aspect, and people both from simulations and observation, this is relatively well understood. But this is not the case when you go to the low mass galaxy. Okay, before going to that, in massive galaxies, one other thing we see is that, like, this is again the enhancement in star formation rate as a function of separation. So this is the merger, and this is the interacting systems. So the one on the closed circle is the central star formation rate from the SDS's 3 arc second fiber, and the open circle are the star formation rate from the outer part of the galaxy, like outside the 3 arc second. So here you can clearly see that at any stage of interaction, the enhancement in star formation mainly happens in the central regions of these massive galaxies when they interact. So this is something which we have to remember. We will come back to it in terms of low mass galaxies, how different or similar they are. Okay, so we don't know much less studies on mergers and interactions of low mass galaxies, and this is mainly due to challenges in observations as well as simulations. But why do we, so we are now slowly trying to understand it better based on better data and better simulations. So why do we even care about dwarf galaxies? Can't we just extrapolate the results that we have from the massive system? But it is not possible because these are low mass galaxies, shallow gravitational potential, and more prone to environmental effects. So this may not react in the same way as massive galaxy interactions. And then why do we care about dwarfs? Because they dominate the galaxy population at all redshift in the universe, and the hierarchical or the lambda CDM model of hierarchical galaxy formation predicts that the mergers can happen at any mass ranges. So it's a scale-free phenomena, and majority of the mergers at all redshifts are expected to be between low mass galaxies. So because of all this, like, it is essential to know how low mass galaxy interactions affect evolution. Okay. So many of the dwarf interacting systems which people study are mainly focused on individual systems. One of the nearest, and also they mostly will be in a satellite system, like you will have a massive host and there will be dwarf interacting satellites around it. One of the nearest one, and my personal favorite, is the Magellanic Cloud. This is the nearby galaxy, which is at a distance of around 50 to 60 kiloparsec, and as they are nearby, you can resolve individual stars. And this is a figure where it's an optical and radio combined image. This is our galactic plane, and these are the two galaxies, the white spot, and the pink one is the H1 data. So you can see that there is a clearly interacting system. And the study of this system has been shown that the dwarf interactions, mainly between these two, can enhance star formation, create substructures like warps in the disk of the galaxy, and many other results. There is a lot of studies in these objects. But however, in the context of to understand the effect of dwarf interactions, this is not an ideal target because they just don't interact with each other, but also interact with the Milky Way. So there could be effects from the massive host in their properties. So this is not an ideal target. So what we need to do is, for the isolated dwarf systems, they are the best probes. So there are, like, individual systems which are studied in these papers, like where there is no massive galaxy nearby, and how galaxy interactions, just the dwarf interactions, affect their formation. So there are other studies also. There are previous studies with of interactions which suggest that they can increase the star formation rate, and also it can both trigger as well as prevent star formation. And but one of the drawbacks of these, as I told, it is mostly individual system based. Even with the one with a larger sample, like these are mostly based on galaxies which are at the around 10 to the power of 9, which is at the upper end of the low mass regime. Then also most of these studies are based on optical. So lack of dedicated UV studies of these systems to understand star formation properties is essential because UV is the best tracer for star formation. So in this context, we are doing a couple of studies here. So I'll go to these in the next slide. So you heard a little bit from Rakshit yesterday about this post-merger galaxy effect. I'll just go through them kind of. So we are mainly looking at the mass range 10 to the power of 6 to 10 to the power of 9.5 in these different samples. Okay, so the first one is the one based on Galax data on the lens cancer void. So these void regions are the underdense region in the universe, and like many of them are don't have a massive host nearby. So we selected a sample of around 58 dwarf galaxies in this mass range with no massive galaxy within a 3D volume of 2 to the power cube. So this is taken from this paper, and out of this 58, 22 are interacting. There are different stages of mergers. Based on H1 maps and indications of morphology in the optical images, etc. And 36 are around isolated dwarfs. So when you have this, we took the galaxy image of it, the FUV band, which is a tracer for star formation. This is a tidally disturbed galaxy. This is like a pair. There's a massive here also. It can be of different masses, and this is a kind of relatively isolated system. So we estimated the star formation rate for all this system, and what we get is that. So the plot here on the left is the stellar mass and star formation rate, and the open circles are the isolated one, and the one on the black stars, or the fill stars, are the interacting dwarfs. So what I meant by all of them are away from massive galaxies, but these are in pairs or mergers, and these are like isolated dwarfs. So here they are all within the 1 sigma line of the star forming main sequence. But if you take a small bin of around 10 to the power of 7 to 10 to the power of 8 solar mass, where we have relatively large number of sample, and calculate the median star formation rate for this particular mass bin, like you can see that there is around the mergers or interacting systems are around 3 times more enhanced star formation rate compared to the dwarfs in the isolated one. So this matches with some of the recent simulations which predict that they can drive moderate to 2 to 4 times star formation, increase in star formation in low and high intermediate redshift. So these are very local, around 18 megaparsec distance from us. Okay, so now once we have it, what we wanted to do is, like, this is based on Galax. So Galax we can do only this integrated star formation rate like this, but we can, if you want to probe more details of the spatial distribution of star formation, we want to go to higher UV images. So in this context, we proposed a FAR-UV survey of around 22 interacting dwarfs and 12 isolated dwarfs using UVIT. So this is many of all of you know about this. The UVIT has around 3 times better resolution than Galax. This is clearly shown here. This is one Galax field, and this is around you can see 2 blobs here. So it's a highly resolved compared to Galax. So we also have like a complementary data from other optical facilities so that multi-wavelength data can be studied. So this is the PhD thesis of Rakshit. So now here, this is a UVIT image. This is one entire 28-minute field of view, and you select the galaxy. You identify the star forming clumps here. So there it was just one structure. So here we can have multiple structures. For each of these star forming clumps, you can estimate the star formation rate. This is for the image, so you can get the star formation rate. You also normalize this with the size of the clump, because the size of the clumps are different. So accordingly, the flux will be different and the star formation rate can be different. So you normalize it with star formation rate, the clump size, so that you get the star formation rate density. So we did this for many of these systems. So this is one galaxy. So this is the one which shows tidal features. This is one without. So there is less number of star forming clumps here, but you can clearly see that the star formation rate density here for the same mass and the same distance galaxy with different features, just the interaction and non-interaction, there is a change in the star formation rate, enhancement in star formation rate as well as in star formation rate density. So this was done for around 26 galaxies, and this is the combined plot where you can see the star formation rate density for many of these clumps as a function of radius from the center. So you know how the spatial distribution is there. So individual points are different galaxies. So this is the median plot here. So this is for the interacting system and this is for the non-interacting system. So they overlap, but overall there is a increase in star formation rate density at all all distances from the center. It is not just on the center, but all over. There is an enhancement in the, and it's almost equal as well. So this is one of the results. And then yesterday Rakshit presented, we also looked at some of the post-merger dwarf galaxies up to a redshift of 0.1 using the around 200 post-merger dwarf galaxies using Galax. There also we found the enhancement. So this x-axis is the enhancement in SFR with respect to non-post-merger galaxy matched in mass and redshift. So you can see that like anything above, this is a log scale. So anything above this is like all showing enhancement. So there are some galaxies which are quenched also, but most of them are like overall there is an enhancement, and different color histograms suggest that the total central and the outer part. So basically in this galaxies, we also looked at the central 3 arc second and the outer just 2 bins. So there also we do see a enhancement, an equal enhancement. So the enhancement factor is similar in the central and outer regions, indicating a galaxy across the enhancement. And this is in contrast to what is observed in high mass regime, which I showed earlier. So this is one of the main results from all the studies that like whether it is spatially resolved or even with Galax things. So there is an increase in star formation rate, but also when there is an interaction, and also this is happening across the galaxy, not just concentrating on the central region. So now what is the physical process for this kind of enhancement in galaxies? So in the massive galaxies, what happens when there is a merger, like because of the gravitational tidal torque, the gas funnels to the center and it enhances the star formation. So here this galaxy is being shallow potential. This may not be happening, but overall this enhancement is happening because of the merger driven processes. So what is so one of the earlier papers by Chanda mentioned something similar, like about this merger, how the galaxy wide star formation can happen because of mergers. This is basically the ISM curve compression due to the merger induced turbulence. So this we are just trying to connect with another project of my student, which is so what happens during mergers? Mergers inject turbulence, and there are other sources of turbulence like stellar feedback, galactic shear bars, etc. And now this turbulence can stabilize large clouds, stabilize clouds on a larger scale, but it leads to fragmentation. So this is something schematic where it shows like how it fragments using energy cascade, and it can lead to this hierarchical clustering that you see in ISM, like the denser structures, smaller structures surrounded by less dense, larger structures. So this is a key observation in all the star forming galaxies, and this kind of hierarchical structuring depends on the factors which are injecting turbulence to these systems and which is creating this. So a study of spatial distribution of young star forming clumps will provide this hierarchical structuring scale, and hence it's a proxy of the turbulence injection scale and the physical phenomena involved in it. So this is not just based on mergers, but this project by Shashank, so he is working on the dependence of host galaxy properties on the hierarchical nature of star formation. Is again using UVIT in one of the so we leverage the UVIT's larger field of view, complete coverage, and measure the clustering properties. So what you can see here, just one galaxy, I can explain the red dots are individual star forming clumps, and this is the HST field of view. So for UV, we have the full coverage. Then based on this, they are hierarchically structured, means like it will show a correlation, and that correlation will be there only up to a scale where the turbulence injection happened earlier. So then this is the scale, like the one that using two-point correlation function, you can find the distance up to which these structures are correlated. So we found that, and then in the initial study, we did a feasibility study using 4 galaxies, and we found a kind of dependence on some of the galaxy properties. So this was extended now to around 19 galaxies. We're spanning a morphology, a diverse morphology, and spanning 4 orders in mass. So these are like different spirals, dwarf irregulars, and massive galaxies. And we do see a stellar mass and the correlation length dependence, and there are some outliers. So we are trying to see what are the causes for it and how is it connected with mergers. And there could be other phenomena which can drive these features. So in future, we are planning for a larger sample, which will include more galaxies and with different morphology mergers and all, and we plan to understand how interactions affect hierarchical properties of star formation. So I'll just read the summary slide here. So we do, and I'll take questions. Questions?
Nice talk. I just want like at some point you mentioned that the galactic interactions for these dwarfs can sometimes enhance the star formation, sometimes quench. So what is the reason behind this kind of opposite thing? Is it dependent on the tidal force or tidal field?
Oh, it will initially enhance star formation, and later, like it will use up the entire. So this even the massive galaxies also, that's what people show. So here, like initially when 2 galaxies come close.
That I understood. I think you cited one of the papers and you just say it can do both the things.
Oh, okay. So this could be okay. In the low mass galaxies here,
yes,
right?
right.
This one. So here, like it can in one of the galaxies there is an enhancement. In the other one, it was less compared to for that much. When there were 2 galaxies, one of them was showing an enhancement in star formation compared to a similar mass galaxy which is not undergoing interaction, but the other one was showing a reduction. So that is what it meant, and this is basically by stripping gas from the other thing, and it could be mostly a kind of transient phenomena. The other one can regain star formation after.
Okay, thanks.
Right, nice talk. Just want to ask, like, in case of when we do inner versus out, so what is the effect of selecting this radius? For instance, you have taken 3 kpc.
Yeah.
You would have done based on RE also or
Oh
something.
yeah. So in the one which is so this one which I showed in the massive galaxies which people showed earlier, this was based on the SDSS spectra, H alpha one. So then that's why this is the inner 3 arcsecond fiber star formation rate, and here it is. So in our case, we can put different bins, right? Like so what in the case of galaxy images, we can't do more than 2 bins because of the resolution. But in the one which I showed using UVIT, we can do. So this is the 0.2, 0.3, 0.4. These are like the ratios, like with the radius with respect to the Hollenberg radius. So for all the galaxies, so if there are similar masses, we expect that it will scale similarly, and you can do it. So how it changes? So we try to change these bins differently, but still this phenomena exists. But more sample will be helpful to see. Final question?
Yeah, very interesting talk. I was curious to know this the turbulence differences in the dwarf and large galaxies. The physical mechanism is mainly the rotate. This potential well is main key driver, or
the turbulence, whatever the turbulence injection, as I told here for the dwarfs, it's like in dwarfs as well as in massive, stellar feedback is one of the main drivers. Then the galactic shear, the spiral arms or bars, that also can create this in the massive systems. Mergers can also do this because of the it is like just injecting a lot of energy, right, to the ISM, so kinetic energy to the ISM. So it can happen, but there are simulations and there are some studies which say that the length scale over which it will inject this kind of turbulence will be different for feedback, and like for feedback it will be a few hundreds of parsec, but in case of galactic shear and all it could be more than kiloparsec, but in mergers it can be slightly higher as well. So that's what we need.
Thank you. So yeah, in the interest of time, we have to move on. Let's thank Smitha.
Thank you.
And we now come to the final talk of the session, which is by Sandeep Kataria, who is going to speak on the evolving feeding mechanisms of black holes.
from galactic bars to cosmic mergers.
Good morning, everyone. It is a very fantastic conference. Thanks, Moshmi and Sudhanshu for organizing this and giving a kind invitation. And it is also always exciting to come back to IA, which is where all this research journey started. And was also nice to see the extension of this campus where we walked yesterday, and it is wonderful for I think people here. So today I will be talking about this evolving feeding mechanism of black holes, where bars and even this merger, which is the topic of this workshop, they are thought to be classical channels. And but how which is more important, we want to see in simulations perspective. So there has been a lot of introduction about mergers and bars, especially yesterday with Shomo. So I think I don't need to give much introduction. Just to begin with, we know that SMBH co-evolved with the galaxy components. So one of the strongest evidence is the M sigma relation, which is the mass of the black hole to the dispersion of the bulge. And then coming to the how do the black hole grow is one of this fundamental question which we have been asking. And there are two channels. One is the merger driven channel, which basically drives gas to the central region, and it can enhance star formation. And as this Smitha also discussed the picture by Cormandy and Kannikat, where this merger driven process is one process, and there is another is secular. So the mergers mainly can feed luminous quasars, which has been which we observe, and the time scale with this is very smaller, around few hundreds of mega to 500 something. And for secular evolution, these are very slow processes. Basically, the internal processes, these non-axis symmetric features like bars and spirals, they can also funnel gas when the gas is available in the surrounding of the galaxy. And it has been thought to it has been seen that it feeds in the lower luminosity AGNs, especially in the late types. But in early types, you can still have a minor merger which can feed this low luminosity AGNs. And these processes are a bit extended compared to the merger driven, which is of the order of few giga to couple of giga years. And despite this picture, observations always conflict about this bar AGN connection, whether presence of bar can enhance the AGN feed, AGN, or the number of AGNs are more in bar or unbarred galaxies. So these observations are conflicting, and that's where we want to give a theoretical picture and want to have a more insight. So here only we start this project. So these are like just to give a big picture. And this is highlighted in this one of the nicest review that in different scales the feeding mechanism works in by different processes. Like for extragalactic scales, it is these major merger, minor mergers, and world flows and harassment. These processes work. And in the galactic scales, we have non-axis symmetric features, and chaotic cold accretion is also one of the process. And when you go to the nuclear region, when the gas comes to the central region, there the gas cannot lose angular momentum very easily. So you need some processes which are thought to be nuclear bars or nuclear spirals. And it has been shown by Hopkins et al. In simulations where very much that these processes are quite active in these scenarios. And when you go to
much lower scales, this is sub-parsec scale, this is a still unsolved problem. Where theoretically we don't have a much understanding, but observationally we are pushing the boundary with this ALMA and JWST, where we are detecting such gas inflows in the very central region. And then how it connects to the torus region is also one of the like frontier problems. Now coming to the motivation for the present work. So we are asking a simple question whether if there's a bar present in the galaxy, whether it will affect the black hole growth or not. Because there are two processes. One is the feeding through the non-asymmetric feature, and then there is a feedback into the black hole, which will pull out the gas. And there's a tussle of war between these two components, and whichever wins and what kind of scenario predicts that. That's the question we are asking here. And then we also further ask the role of environment as well. Whether if the bar galaxy is present in a dense or isolated environment, whether it have a different role or not. So these are the two fundamental questions and simple question we ask. And then we are taking the help of mock universe, which is time evolution of these galaxies. In observation, we only tend to see only one snapshot at a time, but now we have a luxury to see in different, basically different time evolution. And we can also, this is obviously model dependent, but we can always give a feedback depending upon the observation comparison and provide improvement for these models as well. So just to give a brief introduction about TNG simulation, where we look these questions. This illustrious TNG is a successor of illustrious simulations with a lot of refinement with the baryonic physics. And it is mainly run with the ARIPO code, which is a moving mesh code. And for gravity, it is using 3PM method. At large scales, it's used PM method, and small scales, it's used P method to calculate gravitational forces. Then the spatial and mass resolutions are more in TNG 50, which is the 50 megaparsec size. And it is the lowest resolution, which is of the order of 300 megaparsec. So as you increase the box size, you lose the resolution because of the computational time cost and all. And just to mention, the whole data for one of the simulation is around 19 TB. So it's like these simulations are run over millions of CPUs over 8 and 10 months, just to give a computation cohorts idea. So in the first part, where we are asking the bar, can the presence of bar feed the black hole? We use the TNG 100 because we want to have a large sample, and we don't want to lose too much resolution. So this is a good trade-off between resolution and statistical behavior. And to give a just brief background of the black hole physics. So these black holes are feed in these simulations when the host halo mass increases to 10 solar mass, and then seed black hole mass is around 1 in million solar mass. And this the black hole accretes in a Bondi accretion behavior, and which is limited by the accretion rate, which is like radiation pressure balances the gravity. And then feedback modes are basically two type of mode, as the Praswell also yesterday talked. There's a thermal mode, which basically heats the gas when there's a high accretion to the black hole. And there's a kinetic feedback when there is a low accretion, which is very efficient. It will pull the gas. It is like giving a pressure to the gas. So when then these are active, this is defined by this simple modeling, which is if black hole mass is less than 8.5 solar mass, is thermal mode, which is a continuous feedback, continuous heating. And but for this, when it is greater than this, it is a kinetic mode, which will basically drive away the gas. And when this is switched on, then it will regulate the feedback. Basically, it will affect the accretion because gas is being pulled away. Now to come back to the central question, we have to select galaxies, which we typically choose for massive galaxies of around Milky Way like type galaxies. And we choose because they have a rotation in them. So So the mean rotation to the total velocity is greater than 0.5. This is the criteria we use. And we find around 4,000 galaxies. And then we classify bar depending on the two methods which Shomo talked and the other speaker also talked. This is N is equal to 2 Fourier mode and ellipse fitting method. So these authors have already put the catalog in these galaxies. So we choose them. So we have now 1193 barred galaxies and 2738 unbarred galaxies. So yeah, we want to have a fair comparison. So we want to control this sample size. So we use different anchors to control. One is the total galaxy mass. So you can see the galaxy mass is more in the barred galaxies compared to unbarred galaxies. And then stellar mass, which is also a bit much higher in the barred galaxies, which is well known that a more massive galaxy it is more likely to form barred. It fits with the classical picture. And then we have a gas mass, which is lower in the barred galaxies, which is also the case shown in many simulations. And then these are the other parameters with a different combination of these two. So these are statistically different distribution. So once we don't control the sample, we just plot the distribution of black hole masses in these samples at z is equal to 0. And we find like there's a strong dichotomy in the two distribution with almost median differences of the order of 10⁸ solar mass. So yeah, no, actually it is around it's almost the double of that, 0.5 times 10⁷ solar mass. But the black hole masses are for the barred galaxies are much larger than 10⁸ solar mass, which is that like there is a kinetic feedback is switched on at z is equal to 0. But it's not true in the earlier redshift. So just to when we control this sample with the galaxy mass, where we have a similar sample, and we see that this dichotomy persists, so that means this relation is robust in a sense with respect to the galaxy mass. And this mass differences come out to be around 4.5 to 10⁷ solar mass. And yeah, I'm not going into the details here because of lack of time, but and then we use control sample with the stellar mass, which is quite interesting, where we see that dichotomy kind of disappears, which is very crucial because the black hole, this stellar mass is a very crucial parameter. Because when we try to make a sample similar, we are not finding enough galaxies which are in the higher side for unbarred case, and we just are duplicating the galaxies. And then we force and enhance the non-duplication, and still we get this dichotomy disappears. And then we play around with different cutoff limits to upper mass, because there is no unbarred galaxies in higher mass limits. So we find like dichotomy is completely disappearing as you cut off, give a cutoff to 3 solar mass. And this is this suggests that this dichotomy is fully driven by the stellar mass of the galaxies. So which is quite important insight from here. Now so what is leading to this dichotomy is we wanted to understand, and we can follow the time evolution. So we found that the black holes were fed. Black hole was there in the beginning. Black hole started to appear earlier in barred galaxies compared to unbarred galaxies. So whether this earlier presence of black hole can lead to dichotomy. So that's why we checked this mean accretion rate to black hole with time from 7 to 2, where the black holes are starting to appear, where the halo mass increases by the order of 10⁻12 solar mass. And we found that for this time, the maximum black hole mass which can be gained by barred compared to unbarred is 1.4 times 10⁶ solar mass, and which is much less than the dichotomy. So this earlier appearing of black holes cannot explain, which is model dependent, obviously. But most of the bars are appearing at z is equal to 2, and then we look for the same calculation from z is equal to 2 to 0, how much this mean accretion can contribute. So mean accretion is higher in the barred galaxies of the order of 3 to 10⁶ solar mass. And when we multiply with the time, and we get this around 4 into 10⁷, which is exactly same the dichotomy. So these are the summary from this study that indeed the presence of bar statistically can enhance this black hole dichotomy. And this we explained through the enhanced accretion rate. Now, just to quickly mention this, we also looked into a detailed evolution of individual galaxies with one of the student Harsh Uttam from Tirupati. So here we choose TNG 50, which is the highest resolution, and then these are the criteria. We isolate the galaxies. There is no major galaxies with the 10⁷ solar mass, and there is no merger until last 3 gigayear, and there is no sudden change in 30% of the mass due to flyby or so. So these are the criteria to isolate them, and these are the few more galaxies for the this is barred, which is isolated, quite clean evolution, and these are non-isolated galaxies which are having mergers. These are 4, and another 4 is unbarred isolated, and then this is unbarred non-isolated. So we have 4 categories. So let me give quick results. This is barred isolated, where the mainly this growth is proceeded by the bar formation, and as you see, as the bar forms, which is this dashed vertical line, the accretion proceeds. And which is not true in all the cases. Like these 2 cases, most of the accretion is happening. Accretion is this purple line, and this black hole mass is blue line. So you can say accretion is happening before the bar formation. So it is not always the case. So in statistical study, we don't get this kind of idea, but individually we get this depth. So in the non-isolated case, it is this merger, which is also shown with red circle, sorry, red square. It's a triangle circle. And this circle is the minor merger, green. And we can see that there's an episodic increase when there is a merger. And which is also true. Like it's not a sustained growth as you see in bar, which is a secular kind of thing. And for unbarred isolated galaxies, this is like there are actually no internal secular evolution present and no merger present. So there is always this slow growth, slow and secular growth. There is no kind of this is relaxed evolution over the time. So still the black hole gain a lot of mass. And this is the final case where you have a non-isolated unbarred galaxies, where you can see that minor merger and major mergers are the key drivers for the episodic increase in the accretion rate and black hole mass. So yeah, so the picture is not very straightforward, but the key schematic is that environment plays a major role. If you have isolated environment, it is a cold disk, and it will form early bar, and it will prolong the secular evolution of black hole growth. But if you have a non-isolated environment, it will be merger driven. And as the merger happens, it will heat the disk, and it will suppress the bar formation. And then basically the merger driven processes are more important, episodic. And you can see that non-isolated case, this post-event accretion is more, this black hole growth fraction is more compared to the isolated one. But the accretion rate, mean accretion rate are a bit dependent upon when the merger happened, when the bar formed. So it's a very complicated process here. So the summary is that the primary regulation is by the galaxy environment, and morphology only can influence the temporal channel. So it can temporarily lead to this, but main thing is the environment, which also plays an important role. So these are the take-home messages.
Very nice talk. So questions? Start with Smitha.
Thanks, Sandeep. Nice talk. So in this barred, unbarred, the 4 cases you showed, any of them have bulges?
Oh, yeah, they have bulges, but we have not separately look into their different evolution. We don't.
Okay, so there is
There are bulges everywhere.
so there could be kind of co-evolution and like whether how it impacts the bulge evolution.
Oh, so I think as for my understanding, these simulations have not reached to that that resolution accuracy. So I think we have to wait for a next generation resolution for that.
But with P50, you can.
But
The sampling length is 150%.
Yeah, but I'm talking about the subgrid physics, which is more, which has a lot of scope to improve in this, which is like kind of quite heuristic to be more blunt here.
So if you just take your part system, have you explored whether the black hole mass growth is related to your path length or as a function of path length?
Oh, we have not looked at it yet. It's a this is a good direction to look.
Really nice talk. I'm not aware of the literature on this, but what do the observations say about it? Say galaxy mass versus the black hole mass. You showed that plot like, okay, if there is a bar exists or the bar doesn't exist, how do these? There is a dichotomy in the relationship. So can you like, say?
Oh yeah, so there's a huge amount of literature. It's a very good question, and from there only we start. So the good amount of so there are I think Napan et al. And Sisteris et al. Where they look for the bar fraction in AGNs, and so with the if you have a bar sample and unbarred sample, and what is the probability of finding AGNs? These both kind of studies are there, and so these studies are dependent on their sample size. So they have a different sample size and limited by sample size. So there are both kind of results. One shows there is a dependence. Some studies shows there's a 50% correlation and there's a bar, 55 more than 50% correlation, and there's a bar and AGN. And another study shows it's less than 40%. So this is a conflicting, basically limited by the sample size. I see.
The black hole mass calculation is dependent on AGN presence, or you can derive mass without that.
Can you repeat?
So the mass of the black hole against the stellar mass is what we are like looking to probe basically. So can't the black hole mass be estimated without AGN presence?
It's now, yeah, it's a very good question. So I think with the JWST and last telescope coming now, people are dynamically detecting the black hole masses. So yeah, so that's the precise reason that most of the black hole masses are not known without AGN till now. But this is a quite evolving field, and I think recently, last couple of years, there are a lot of measurements with the JWST. So it's a very, I think, wonderful direction to look forward to.
Thank you.
I know there are a lot of questions, but I think in the interest of time, we'll have to stop here. Let's thank Sandeep and all the speakers of this session. And we have how our
So we have a group photo in the West Lawn.
Yes.
so everyone come to.
West Lawn, and then we will be outside auditorium.
Thank you.
This next start, we have Sunday, but there is another class, there is like.
Mike, so did you-
Yeah. And they will
the opportunity to present a talk here. So yeah, so let's start. So in the era of
Do you have the mic on?
yeah,
Okay.
so in the era of multi-messenger astronomy, we observe universe in photons, neutrinos, cosmic rays, and gravitational waves. But yet, there is a fundamental question remain puzzling us that what are the uh, astrophysical engines that are powering the high energy universe? So in this talk, I'll talk about galaxy merger and try to answer that can galaxy merger be a search engine that is powering the high energy universe? Because like galaxy mergers are among the one most transformative phase in the life of galaxies, and it triggers star formation, it drives shock waves, and it injects enormous amount of energy into the interstellar medium. So this is our recent work that we have uploaded on archive few months back. This work has been done in the collaboration with Deep, Shubhadeep, Pooja Bhattacharya, Maushmi ma'am, and Ranjan Laha. So in this work, we are trying to see galaxy mergers in the high energy gamma ray bands using formula data. Now one can ask that why we are interested in the gamma rays. So gamma rays occupies the highest energy band in the electromagnetic spectrum. Also, it helps us addressing some key questions in the astrophysics, like the long-lasting question about what is the origin of cosmic rays and what are the astrophysical objects that are accelerating these cosmic ray particles up to very high energies. Second, it can also help us in the indirect detection of dark matter. It could be a signal of dark matter. As you can see in that image, dark matter can annihilate into some standard model particles, and that they can further decay into high energy gamma rays. One more, the key, this high energy gamma rays can help us in finding the new physics like axion particles and maybe dark photon. So let's first see how these gamma rays produced at the first place. So one process is the heteronuclear process when high energy proton, this is mainly, so the cosmic rays has around 90% made up of like proton. So when high energy protons interact with the target nuclei, this is like IgM, it can be IgM, it can be your galactic IgM and all these things. And when it interacts with the low energy target proton, it can produce pions. Similarly, in photohydronic processes, this high energy proton can interact with the CMB and EBL, and it can produce this lambda delta plus, and that can again produce this pi zero. And further, this pi zero can decay to gammas. The same process also produces neutrinos, but here in this work, we are focusing on the gamma photons. Now, gamma also can be produced by electronic processes. So cosmic ray is also made up of electrons, a tiny fraction, but still it's there. So this can produce high energy photons by inverse Compton scattering. And yeah. So why galaxy merger? So can galaxy merger produce these high energy photons? So there are some theoretically motivated papers which theoretically calculated that yes, these galaxy mergers can produce shock waves that are capable to accelerate these cosmic ray particles up to 10 power 18 eV, and that can further cascade down to high energy photons in the range of hundreds of GeV. Yeah, so this is a pictorial picture of my few last slides. So this is your galaxy merger. They are merging and they are accelerating cosmic ray particles and ejecting some charged particles as well as neutrinos and photons. Now, since charged particles have some charge, so they will get deflected in the magnetic field of the galaxies and astrophysical objects. But here comes photons and neutrinos for the rescue. And since they are chargeless particles, so they directly come towards the Earth. Okay, so to observe these gamma rays, we are using this formula telescope. which is about 200 kilometers from Earth's surface. It is an all-sky survey. Yeah. It works on pair production mechanism. So what happened when a high energy charged particle, high energy photon came, it interacts with the conversion foil, produce electron positron, they cascade down and accumulate the whole energy into the calorimeter. So through this, we get what is the energy of your photon and what is the direction of your photon coming from. Okay, come. Yeah. So this is the Fermi's gamma ray discovery in 10 years. So Fermi looked towards all sky, and it has done so many discoveries, including the Fermi bubble and the galactic center axis. This has been done only by Fermi. Now come to our work. So yeah, so this is the equatorial coordinate sky map of our total galaxy mergers that we are considering in this work. So we use 8 different catalogs, which includes around 31,000 galaxy mergers. Here different colors represents the different catalogs. And yeah, and this is your galaxy plane, galactic plane. Okay, now come to the analysis part. So to analyze these galaxy mergers, we perform a two-step analysis method. In the first step, we are analyzing all galaxies individually, and we are using around 16.7 years of Fermi-like data in the energy range of 1 to 500 GeV. So we conduct a bit likelihood analysis for each galaxy mergers and model all the target galaxy merger as a power law. Using that, we calculated the test statistics that can be calculated from the logarithmic ratio of the maximum likelihood, including signal plus background to only background. Basically, this TS will tell you how significant your signal is. Essentially, more the TS, more your significance. And root of TS will tell you the sigma value. And if it is more than 5 sigma, we consider it as a detection. Okay, so yeah, so after applying careful cuts, we end up with 12-14 galaxy mergers. So we started with around 31,000, and now we ended up on 12-14 galaxy mergers. This is the results from a single source analysis merger. This is TS distribution for individual galaxy mergers. Okay, so here x-axis is the TS value and y-axis is the number of galaxy mergers. The green solid histogram here represents the galaxy mergers, and red dashed histogram represents the TS distribution of blank sky. So blank skies are those sky regions that are away from any known galaxy merger, any known gamma ray sources. Okay, and here you can see, okay, this blue dashed line represents the chi-square distribution, which follows the null hypothesis if your n goes to like for larger n limits. So here you can see that your blank sky distribution is consistently following the chi-square distribution, whereas we can see some excess in galaxy mergers. So that is a signal. Then yeah, and this dotted line at TS equals to 25 shows a threshold for the detection. And you can see that some galaxy mergers are showing us some excess. So these are actually around 8 galaxy mergers whose TS is greater than 25, that is 5 sigma detection. And the remaining 1206 target galaxy mergers are considered as faint galaxy mergers because their TS is less than 25. Yes. Yeah, so yeah. So here is the list of these 8 significant galaxy mergers that I was talking about. And the most significant one is this RCS 233814991. This has TS of around 40, which corresponds to approx 6 sigma. Yeah, here is the TS map in the direction of this galaxy merger. And you can see, so this is like RN deck, and this is the TS heat map. At the center, you can see that there is some excess. Right now, in this model, our galaxy merger is not added. And if I add the galaxy merger here, you can see the excess is gone. That means the model of this RCS that we have added is explaining the axis. Okay. Yeah. Now, since there are few galaxy mergers that are showing significant axis, but still most of the galaxy mergers are faint in nature that I showed, like 1206. Now they can be, yeah. So these faint galaxies may be collectively contributing to the gamma ray sky. So this motivates us to do the stacking analysis. So in stacking analysis, what we did, we created this 2D TS grid for each galaxy merger. So yeah, so this grid is like made up is like x-axis is photon flux, integrated photon flux, and y-axis is a spectral index. And we calculated the likelihood at each point of this grid. That is basically your TS. And since TS is additive in nature because it is logarithmic, so we can add all the TSs, all the TS grids of these 1206 galaxy mergers, and we can find the best fit. So here we are assuming that the spectral behavior of all these galaxy mergers can be explained by average photon index and the integrated flux. Okay, so yeah, here are the results from this stacking analysis. So here you can see the same thing. The x-axis is the gamma ray flux and y-axis is your photon index. And this is the stacked TS profile of 1206 galaxy mergers. And this black cross is representing the best fit value. And you can see that this best fit value corresponds to TS value of 1235. That corresponds to 35 sigma. That is really, really significant signal. And this is, yeah, and if you see the photon index corresponding to this best fit value is around 2.07. That is consistent with the theoretical results that I showed in my starting few slides. Now to check the robustness of our analysis, we also perform same analysis method to the same blank sky regions, 12 blank sky regions. And here you can see the total TS max is only 14. You can compare it with the galaxy mergers, which is nothing. And also the best fit index value here is 4, which is representing the background fluctuation. It cannot be because of the astrophysical sources. Yeah. Yeah, here I showed the stacked SED of these galaxy mergers. This stacked one, right? So this blue one is the SED in 7 logarithmically spaced bins, energy bins. And here also you can see that we didn't get any upper limit. We get a signal in all the energy bins. So galaxy mergers are consistently emitting in the whole energy range that we are considering. Also here also you can see the best fit index is this and the flux is this. And the both of these values are consistent with the theoretical values. We also showed the SED of the highest significant source, this RCS 2338. And here this orange and red line represents the 5 sigma sensitivity of the CTA telescope. And you can see that that this RCS one can be detected by CTA. And not only this one, maybe few those significant galaxy mergers can be seen through CTA in future. So here I'm concluding my talk. So these are the summaries that we found 8 significant galaxy mergers. Now here's an update that in recent catalog of Fermi, we found that out of these 8 galaxy mergers, 5 they also found, and out of these 5 galaxy mergers that they also found, 3 of them is unassociated. That's mean they are not associated with any other sources like Blazar or FSRQ or these things. So it could be an interesting result that it could be a galaxy merger. Now from stacking, we found that there is a total TS is 1235 that corresponds to 35 sigma detection. One thing that I didn't show in the slides is that we also found that there are 18 unassociated sources from Fermi that are associated with the galaxy mergers. So that could be the same thing. Yeah. Now, although the best fit spectral parameters are consistent with our theory, to say that whether it is from the shock wave or whether it is from the star formation processes, one has to do the multi-messenger thing here also in IR and radio or something. So yeah, thanks.
In the interest of time, one just quick question.
So,
Discuss later.
high energy gamma radiation from galaxy mergers.
Yes,
The plot that you showed, yes, distribution has shown background as regions without any gamma radiation. Right?
yes.
So did you look at just galaxies which are not undergoing mergers?
No, we
As a
didn't.
comparison.
No, we didn't look at.
That should be.
A check.
Tell you that whether
It's
galaxy
a-
mergers are producing high energy gamma rays in excess of.
Yes,
normal
yes,
galaxies.
yes. Yeah, I see. Yeah, but we didn't check this thing.
Hi, thanks for it was a great talk. Can you just tell what were the weights assigned while stacking? Like
Sorry.
Weights assigned.
Sorry.
Weights
weights,
assigned.
like the stacking,
Yeah.
what were the weights assigned? Yeah, how you, so was it like the most massive nearby ones were stacked first and then you went as n by z square kind of thing?
No, we just check all the, I see your point that you are saying that maybe the higher significance ones are contributing much to that,
Yes.
right? Yeah, no, actually, we didn't weighted the things. We just tagged all the galaxy mergers, but we checked few things that if you remove a fixed number of like galaxy merger, let's say these are 1200, we also check with 800, and then your TS is like also going from 1235 to somewhere around 800. So it is really not.
Okay, thanks.
Yeah.
The reason I said that because we did a similar study for galaxy clusters. When we stacked them randomly without
Yes.
any weight, the TS was different than when we stacked them by weight. So when we stacked them by n by z square, the TS decreased, but when we stacked them randomly, the TS increased with very high significance.
So you weighted only on the basis of the distance, right?
I
Yeah.
think you take it to a.
Yeah, but most of these galaxy mergers are at the same redshift. Yeah, so that thing will not make any difference. Yeah.
Okay, so let's thank Jaya for a nice talk. Our next speaker is Ayisha Fida. She'll be talking about investigating GPS and CSS evolution at the centers of ULIRGs.
Am I audible? Yeah. I'm Ayisha Fida. I'm a PhD scholar at MCNS Mahe. I'll be talking here about some part of my PhD work, and the title is Investigating GPS CSS Evolution at the Centers of ULIRGs. And these are my collaborators of this work. And contents, I'll be talking about introduction, a bit about the radio loud AGNs and the young stages, evolutionary stages of radio loud AGNs, and the objectives of my work and methodology and results. So I'll start with the active galaxy. So basically, active galaxies is luminous at the core part, which is called AGN. And this AGN is classified on the basis of broad optical emission lines and viewing angle and the radio power. Here I'll be focusing on the radio loud AGNs, which is classified based on the radio power. And these are, okay. So these radio loud AGNs are very powerful galaxies which emit jets which extends beyond the centers of the galaxy, and plus this jets spans from kiloparsec to megaparsec scale. There are some studies shown that the compact steep spectrum sources CSS and the gigahertz peaked spectrum sources GPS sources are the young evolutionary stages of a radio loud AGN. Basically, the compact steep spectrum sources, the linear size is 1 to 20 kpc, and for their spectral property, the turnover frequency peaks around few hundred megahertz. and the gigahertz peak to spectrum sources. These are a bit smaller version of the CSS sources, and the linear size is 0.1 to 0.1 to 1 kpz, and the turnover frequency peaks around few gigahertz, like 1 gigahertz. And but the recent studies, Norris et al., Nandi et al., shown that the ULUX ultraluminous infrared galaxies are the young stages of the GPS and CSS sources. The ULUX are the major system which highly opaque dusty center nuclear regions. So both the starburst and agent activity supply power in this system, but it is still unclear which activity is dominating here and how these two activity affecting the whole merging process. So we expect there will be a link, evolutionary link is connecting between the ULUX and radio galaxy. Basically, ULUX have three merger phases. First is pre-merger phase, when the two galaxies are going to merge, and here the two galaxies have agent. We will be getting dual agent system here. And merger phase, ongoing merging process will happen in this phase. And if the two galaxies have agent, we will be getting binary black hole systems. And the post-merger phase, this phase we are expecting the CSS and GPS's growth. And the objectives of my work: provide direct observational evidence of ULUX as a natural progenitors of young regions, and identify the close agent pairs in ULUX, investigating their potential interactions and co-evolution, to examine evolutionary scenarios of young regions, distinguishing between the youth-driven and jet frustration. So there are basically two hypotheses for CSS and GPS sources based on the compact nature. The youth hypothesis tells that CSS GPS sources are young radio loud AGN, and radio jets propagate outward, and they will expect to grow into the larger radio galaxies. And the frustration hypothesis tells GSS and CPS sources are confined by the dense interstellar medium within their host galaxy. So the jets cannot grow from the center of the system because of the interstellar medium is surrounded by it. So it is blocking the jet's growth. And some of these sources may never evolve into large scale radio galaxies also. And the spectral properties of GPS and CSS source, you can see in this figure. So basically, this is optically thick region where the synchrotron self-absorption happens, and this is optically thin medium where the synchrotron emission happens. So we will be having a turnover frequency, which is basically a transition stage from SSA to SE. So this turnover frequency, if it is peaking few hundred megahertz, this is that will be the characteristics of the CSS sources. So we expect for the sources in our sample, this spectra. And the methodology and results. So the sample selection, we first carried out the studies with 38 ULUX. We selected from the main sample, Kim et al. 1998, which consisting of 118 ULUX. So we selected the 38 ULUX on the basis of detection in NVSS and RETI-GSS. And this sample includes 13 sources from Nandi et al. Also. And you can see the distribution of the optical nucleotype of the 38 sources in our sample. The majority of the sources are coming safer to us. And these are the all 38 sources. And the filled 13 sources, blue color, which are the 13 sources from the Nandi et al., which are also a part of the main sample. And what is this green line and red line? I will come to the next slide. So I'll explain about it again. And the data collection for the 38 sources, we have collected all the available radio archival surveys. And these are the surveys we have used. And also we collected the UGMRT band 3, band 4 sources, very few sources in our sample. And this is the band 3 UGMRT and UGMRT band 4 results. So you can see that most of the sources are showing the compact nature, but very few sources we got minor eccentric structures and radio spectra. So we fitted for 30 sources in our sample, the radio spectra, and I will explain this one. So this source, you can see the synchrotron self-absorption happening and the turnover frequency, which is nu max 140 15 megahertz. So this is a characteristics of CSS sources. And again, the emission part is happening. And you can see the break frequency, which is 4.8 gigahertz, which is very high. So for the young sources, we are expecting high break frequency based on this equation, the synchrotron age. So we have estimated the age for all the sources, and the spectral age of the sources. 19 sources are coming, which is less than 5 megahertz, which is very young. And 17 sources showing the low turnover frequency, 63 to 509 megahertz. And we also did a radio to FR correlation analysis study. So this study is basically tells that according to Unital, Q is equal to 2.34, which is a criteria to understand the sources is showing star burst characteristics or the radio excess characteristics. So we have calculated the Q value for all the 38 sources in our sample at 1.4 gigahertz. And these are the sources, all the 38 sources, and the red line which indicates the Q is equal to 2.34 criteria, and the green line is the average Q value for all the sources in our sample. And the sources are color coded with the age synchrotron, and you can see that majority of the sources, there are 93% of the sources is coming below this red line, which indicates the radio excess characteristics. And and those sources are showing young age also. And the sources which comes above this, which are showing star burst characteristics according to this criteria, but we are not expecting the sources will be showing the young age. But you can see there are 4 sources are showing the young age, and when you go to the second panel, these sources are showing the turnover frequency also. So the filled circles are in the second panel, it's showing the turnover frequency presence, and the not filled are not turnover. So the sources which showing the high star burst characteristics, we are not expecting it will be showing the young age and low turnover frequency. So we confirm these 4 sources which comes above this criteria. We confirm these 4 sources are buried agents, where the agent is hidden by the dense dust and gas surrounding by. And we also did the voice color cut analysis. This also a criteria according to Blecher et al. So 0.5 is the criteria. We have collected the W1, W2 values for all the sources, and we did the W1 minus W2. So if the values are coming above the 0.5, it will be showing the AGN presence. If it is coming below the 0.5, it will be showing the starburst characteristics. So we did for all the sources in our sample, and this is the new study we did. This is device and radio synchrotron age. Any relation it is happen, if it is any relation is existing between the radio synchrotron age or voice. So we did for the 38 sources, and these are the median lines of the radio synchrotron age. The blue line indicates the median of the age, which have the voice value less than the 0.8, and the red line, which will be the 0.8 greater. So we can show very small variation of the median lines here, because we have very few sources in our sample 38 only. And we did the pre-merger and merger classification. You can see this is optical based, and you can see majority of the sources are in merger phase. So we did the comparison study of the optical merger and the voice also. So the sources which are showing optically merger or post-merger phase, they are having voice value higher. And so these are some interesting sources in our sample. And this source is optically is a single nucleus system, but in radio VLA 8.4 gigahertz, you can see that 3 compact structures, radio compact structure, but we don't know whether it is a one radio galaxy with one pair of lobe, or is a 3 different radio compact structure. And this also, so the source also is a triple nucleus system in optical, and in radio we are getting 2 compact radio structures. But interestingly, in the northern component, Nandi et al. Found that the optical double peaked emission lines, which are expecting to show the binary systems, And this source also very interesting. This is also a triple system in optical, very disturbed morphology, and the GMRT 1.28 gigahertz, it's compact emission lines only getting, but this also showing the double peak emission lines. So we did the VLB observation for the few very interesting sources which we are expected to get the binary systems, and we got the detection for the sources. So the source also already Daniel found that the double peak emission lines. So the VLB a 5 gigahertz image. We can resolve this to component with a parsec scale, 25.3 parsec scale separation at 5 gigahertz. And the 8 gigahertz is also we are getting the same two component very separately 10.4 parsec. And what we did, we have estimated the peak flux, integrated flux, and the spectral index. So we named the two components A and B. So the A component spectral index is getting minus 0.13, which are normally to show the radio compact course. And the source, the component B, we are getting 0.38. So this spectral index we are expecting for the high frequency pickers, which are also a compact radio sources, but their spectral turnover which peaks above 5 gigahertz. And we also did the brightness temperature calculation for component A and B separately. So these are also, according to the results of the brightness temperature, these are also indicate compact emissions and the AGN activity is going according to Hayashi et al. And the work on the remaining sources. So we already studied the 38 sources. Now the remaining sources in the sample, we already started. From the 73 sources we have selected. Based on the NBSS and VLSS first RAX loads detection. So here you can see the 73 sources and their Q value, average Q value, and the 17 sources in orange circle mark. There we went for the UGMRT band 3 observation. It is already done for 14 sources and remaining is there. Why we went for UGMRT observation? Because these sources are showing turnover characteristics. So we are missing out frequency coverage from loads to racks. So that's why we went for the band 3 observation. So the main conclusion of the first phase of the study, the results indicates main energy source in the system is AGN activity rather than the star formation. Many of the ULIRGs are evolving into the compact steep spectrum sources with a young age in the post-merger phase of the ULIRGs. And we note 4 sources with a high star formation activity and very low turnover frequency and less age, and the sources we confirm for buried agents. So our study enables us to trace the evolutionary link is connecting between the ULIRGs and radio galaxy. Thank you. Okay.
I have one question about these star formation rate. About you told how large it is in these galaxies.
Star formation. Normally, I did not do star formation rate, but normally the star formation rate 10 to 100. This range is coming for this ULIRGs. Yeah, but I did not do separately, but it's already previously studied it. So in this study, we are mainly focusing on the radio observations because there are ULIRGs people studied for in infrared and optical wavelength. So radio will be the main focus.
Yeah. What fraction are AGN in your 38 sample?
In 38, agents.
What fraction number?
There are like we are getting the buried agents for other all the remaining sources are AGN only character. Yeah. Yeah.
If there are no more questions, let's start. Oh, sorry. Yeah. Last.
How do you confirm they are in the post merger?
Oh, okay. Very good question. So why we confirm in the post merger phase? Because in the like here, there are some studies showing that the CSS and GPS sources evolution from the post-merge phase, so like late merger phase of the ULIRGs. And this sources we have we are seeing some characteristics of that spectral properties that peaking at few hundred megahertz and few gigahertz. So this is the characteristics of CSS and GPS sources. We are not expecting showing to the other sources. We are expecting this will be showing in the young radio galaxies. So this phase, and also the ages are very less. And yeah.
Thanks, Aisha. Let's thank Aisha for a nice talk. Let's move to the next speaker. It is Sougata Sarkar. She will be talking about comparative study of dark matter, halos, and nearby galaxies.
So, hello everyone, I'm Sougata from IIC. Today I'm going to talk about comparative study of dark matter halos in nearby galaxies. Although this is not directly connected to the galaxy mergers, but to know about it basically connects the gravitational framework of galaxies by studying H1 kinematics and dark matter halo profile. And it is also important to understand for galaxies to completely understand the what mergers will do to the galaxies. So let's start with the brief overview of my talk. So I'll start with introduction and I'll talk about the methods I have used in result and conclusion. So we all know about that the missing mass problem, which is basically the discrepancy between the luminous matter and the gravitational matter. So, which is evident from the rotation curve of galaxies. So, from the theoretical aspects of rotational curve, it is expected that the rotational curve at higher radii it should be flat, but from the observation, follow with radius, but from the observation, rotation curve become flat at higher radius. So, which basically tells us that there is a mass discrepancy of the galaxies. So, this thing actually led to the idea that galaxies are embedded with dark matter. Hello, though there are also other explanations for this discrepancy, which basically the modified gravity, and I won't go to that debate which one is more correct. So this picture tells us about the merging of two clusters. So this pink region, basically the X-ray luminosity, which corresponds to the hot gas of the baryonic matter of those galaxies, and this blue region is coming from the gravitational lensing, which basically tells the gravitational matter present on that galaxy. So see, during the merger process, what happens? The baryonic matter interact with each other and they got slowed down during the collision. But gravitational matter or dark matter, they don't interact with each other. So they left as it is. So this is the one of the important proof for dark matter. So yeah. So now the question is this: how these galaxy halo are shaped, or the dark matter structure of in galactic scale. So from the lambda CDM cosmological simulation, which predicts that dark matter halo in galaxy should be in a like Caspia profile, which has a slope of -1 in the inner region. Whereas from the observation for dwarf and lower surface brightness galaxies, which are thought to be the dominant in dark matter, galaxies, and they have shown that these observations, the dark matter profile of these galaxies are core profile. That is, it has a inner density slope of 0. So this discrepancy of observation and simulation is called the cascode problem. So it and this cascode problem has 3 different type of solution. One is itself the nature of dark matter that we are using, because from lambda CDM simulation, it assumes that the dark matter are the cold dark matter, not their. And another part of this explanation is the inclusion of baryonic physics in those simulations, and the another explanation is the systematics. That means when we estimate the dark matter or mass distribution of a galaxy, we do it through a proxy, which is the rotation curve. That is this rotation curve of a galaxy gives you the mass estimation over a galaxy. To analyze properly the rotation curve, it is very important, and that will give you the accurate estimation of mass. So I work on the systematic problem. So earlier, people are calculating this rotation curve using a 2D method where they have used the velocity field of H1 or other probes data cube of galaxies and calculate the rotation curve, and that fitting the tilted ring model. This tilted ring model are basically the it assumes the galactic disk as a concentric ring, and each ring has its systematic velocity, position angle, inclination angle, etc. Now the problem with the 2D method is that it has some systematic errors like projection effect, beam smearing. So to overcome that effect, people tried with the 3D kinematic method where people uses the direct the 3D data cube and use the tilted ring model and model the galaxy to calculate the rotation curve. And this work that has been done by Sushma, she has shown that if I use two different methods for 2D and 3D rotation curve, it clearly shows that the mass distribution of galaxies has been different for two different model rotation curve. So which basically tells you that we need to be very cautious while calculating the rotation curve, and we need to use the more robust way, the 3D kinematic model. And also there are other studies which already tells that not only this work, other scientific science cases also affected by this rotation curve. So this 2D rotation curve. So it's very important to use the 3D rotation curve. So until now there are very few work that has been done using the 3D kinematic model. So with this motivation, we have started a survey which includes around 500 galaxies. The aim of this survey is that to uniformly analyze all these archival GMRT data and do 3D kinematic model on that and revisit those science cases that has been done with 2D kinematic model rotation curve. So this science is the one of the part of this overall project, and we have used the first pilot sample of this project. So for the mass modeling, this is the data product of galaxy of our sample. So this is the integrated spectra. This is the moment zero map, which basically tells you the integrated H1 emission overlaid on the optical image, and you can see that the H1 is more distributed towards the larger radius, while the dark matter is dominant. So H1 is a very good proxy for these dark matter related science cases. And this is the moment one map, which is the velocity field of a galaxy, and this is the moment two map, which tells you the velocity dispersion of that galaxy. So for the mass modeling, we have used 4 different type of profile to see the how galactic halo look like in the inner region. So we have used a very basic NFW profile, which has the inner density slope of -1. Then we have also used 2-port profile, pseudo isothermal and Barker, which has inner density slope around 0. And this ionosphere profile, so we have used this profile has an extra parameter. So if called the shape parameter, if you change the value of that shape parameter, according to that, it will have a different shape in the inner region. So we have used this shape parameter such that it lie between these two different other port and cast profiles. So in summary, we have taken 4 different type of profiles: fast, port, and intermediate profile. And we have modeled the total rotation curve or total velocity in 3 different main component of galaxies. One is the gas part, and the stellar part, and the dark matter halo. This gas part has been calculated from the 3D kinematic model. We got the H1 surface density, and we have used that surface density to convert it to velocity, not using any previously assumed model. We have directly used that value. And for the stellar part, we have used 3.6 micron data, so which is a very stable when we need the mass to light ratio and give you a more robust or accurate representation of stellar part of a galaxy and the dark matter halo. So in our analysis, we have used Markov chain Monte Carlo, and the free parameters of our models are mass to light ratio, the mass within a radius, the R200, this is the M200. This R200 defined by in a radius where the density is 200 times the average density of universe. So, and the concentration parameter, which is a ratio of this R200 and scale radius, which basically tells the compactness of your profile. So, this is the first. So, this is the mass modeling of using NFW profile for Galaxy NGC 7800. This is our rotation curve. This one is the model rotation curve, and this blue one is the dark matter component of the velocity, and this is the stellar part, and this curve basically tells you the H1 gas part. So, and this is the posterior distribution of our modeling, and the corresponding parameter has been shown here. Now, this for the same galaxy modeling using Ayisha profile, Barker profile, and the pseudo-isothermal profile. So here is the overall result of our analysis. We have used 11 galaxies here, different colors for the different galaxies, and this plot basically shows the mass flight ratio values for 4 different profiles. This one is the M200 value for 4 different profiles, and this is the concentration parameter. So for the mass flight ratio at M200, we almost get more or less similar values for 4 different profiles, and also same we have seen for the mass M200 also. So for to consistency of our analysis, we check this for stellar mass and halo mass relation, that we see that for 4 different profile our, and these other points are from the other analysis. From one is from the spark sample, another this TAS and Mansilla Pinnacle. So we have overlaid all the other works, and this is the scaling main relation, and this is the main samples, 11 samples. So we have seen here for more or less 4 profiles, we are seeing almost they are aligned within the error parts of this relation, and that basically tells you a correctness of our modeling. And there are 2 galaxies, they are slightly deviated from this main relation, which is rely on the point where this the variant deficit dwarf. So this has been done using the Mansira Pina et al. So they have told that for some these variant deficient dwarfs, these galaxies are variant deficient, and they lie below this relation. So we see 2 of our sample like coming in that region, but to completely comment on this, we need to do a better or more detailed study on those galaxies. So from the chi-square reduced chi-square distribution, we have seen that for most of the galaxies, half of the galaxies are preferring fold profile and half of the preferring Caspi profile. So from here, we can't conclude that which profile is being preferred for our sample. So for that, we need a cross check. We have what we have done. We have used all the modeled dark matter, and we have done use the observed velocity, and we subtracted all the baryonic component, and use that dark matter component. So we compared these both non-parametric and parametric dark matter to see how they are if they are matching or not. So these are the rotation curve for dark matter component for parametric and non-parametric dark matter, and these are the mass distribution for all the profiles. So in this profile, you can see here for only the NFW profile, from the inner to outer region, these 2 different like this model dark matter and this subtracted dark matter are matching with each other in a very good way. But if you go to the core profile, in the inner region, you see a discrepancy. So from this, we are concluding that maybe for our sample, our galaxy, they are preferring towards the NFW profile, not the other core profile. But we can't say it statistically confident way, because our sample size is very low. It's 11. So that is why we have started our next work, where we are increasing the samples with more galaxies. We are including almost like 22 plus 10, and the overall sample will be around like more than 40. So for that, mass modeling has been already done, and soon we'll publish that also. Then we can also say about this trend, that if it is NFW or the code profiles. Yeah, this is the conclusion of my work. And for one interesting point, that this is one of the interesting galaxies from our next Garcia 2 sample. So one paper that has been already claimed that they are interacting, but we don't see that kind of interaction here. But we need to see in detailed way. And thank you.
Thank you, Sougata. Very nice talk. Questions?
In your sample, all are non-interacting galaxies?
Yes, mostly, but there are some galaxies like for the next sample that we are already make the new sample. There are some of them they have one or two components, but we are not sure that if they are interacting or not because we did not see any H1 breach between them. Because maybe they are almost like similar in region or redshift in same redshift two galaxies. Maybe that may be the case.
So what is the mass range of your galaxies?
So the stellar mass range is like almost 10 to the 8 to 10 to the 10. One galaxy has 10 to the 8 in order. Yeah.
This is more pronounced in the lower side of the mass galaxies. Okay.
So just, I have one question. So about this mass to light ratio, which you showed, one of them was outlier, right? In that, like.
Yeah, so there are two galaxies that we are not using 3.6 micron data because we don't have. So for that, we are using R-band data. So
That's why that.
yeah, exactly.
Okay, thanks, Sougata. Thanks for a nice talk. Let's thank Sougata. And let's move to the last speaker of this session, Avinash Kumar. He will be talking about Tick-tock, a supermassive black hole.
Yes. Okay, good morning, everyone. My name is Avinash Kumar Palladi, and I'm currently a PhD student at IISc Bangalore. And today I will be talking about a supermassive black hole binary candidate, which we call as Tick-tock. And this work has been done in collaboration with several people who are mentioned here. And I will start basically with what are supermassive black hole binaries. So supermassive black hole binaries are the binary supermassive black holes which are formed as a natural product of galactic mergers. And they can't be resolved because they are very far away and they are very close to each other. So we need to rely on indirect methods to detect them. And one of the most prominent method to detect them is the periodic variation in the AGN light curves. And recently in 2022, Jiang et al. Has published a paper in which they saw this particular AGN, SDSS J1430 16 plus 230344. And they see that in this particular AGN ZTF light curve, where the blue points are the G band data and the red points are the R band data, we can see that there is a periodic structure here. And this periodic structure has been inferred as a supermassive black hole binary candidate. And here, as you can see, the periodicity has been decreasing very rapidly and from around 1.5 years to few months within a span of 3 years, which indicates that this particular supermassive black hole binary candidate might have been very high eccentricity. And they also propose that this particular age supermassive black hole binary is going to merge in 2025. And so we have conducted an independent analysis of this same data by considering the piece as the periastron passage. And then we have fitted it with a post-Newtonian model. And we found that this, to have such a rapid decay in the periodicity, we should have a very high eccentricity, which turns out to be around 0.95. And since it is a very high eccentric merger, and which is going to merge in the within next few years as they have proposed, it is a very interesting candidate for PTA to study its memory, gravitational wave memory signal. And it will also be interesting for LISA if it would have been here right now. So since this particular candidate is considered to be very high orbital eccentricity, it is possible that it may be a result of a recent galactic merger. And so we have conducted a H1 observations to see if there is any disturbed H1 morphology. So this is the example of a H1 analysis which have been carried out by Kaur et al. I think it's not here. In this particular paper, they have found that one of the FRB is coincided with a galactic merger as shown here. And this is the H1 map. And H1 is mainly suitable for this kind of analysis because it extends far beyond its stellar structure, and also it takes longer time to relax after the galactic merger. So we have estimated what is the H1 mass and the diameter for this particular galaxy, and it turns out to be around 2 into 10 power 10. So the expected H1 mass turns out to be around 2 into 10 power 10 solar mass, and the expected diameter is around 84 kiloparsec, which is around 54 arc seconds. And assuming a H1 line width of 200 kilometers per second, the expected flux density is 3 millijoules. And we have proposed to observe this galaxy for around 33 hours with UGMRT. And we have considered observed this galaxy in this frequency range, 1290 to 1340 megahertz, with a spectral resolution of 2.75 kilometers per second. And we have used CASA to analyze this particular data set, and I will skip the details of this. And these are the calibrations we have got. So this represents the amplitude versus UV wave, and this is for the flux calibrator 3C286, and this is for the phase calibrator, and this is for the field Tick-tock. And the phase and the flux calibrator seems to be nice. So we have proceeded to make the image of this particular galaxy, and this is the source we have seen. So we have not seen any extended emission or any jet emission, and we only see a point source with the same resolution, with the same 2 arc second resolution with the GMRT. And the flux density we have found to be around 1 millijansky, and we have compared it with previous data in the literature, and it is consistent with that. And then we have proceeded to do the spectral line analysis, and we have not found any indication of 21 centimeter line, and we think this might possibly a gas poor galaxy. So we have proceeded to forward to put upper limits on this particular galaxy, and for this study, the targeted H1 5 sigma H1 column density is 1.7 into 10 power 20 centimeter per centimeter square, and the upper limit we have got is 5.3 into 10 power 19, which is less than the estimated column density. And we have found the upper limit on the mass is around 2.9 into 10 power 9 solar mass, and the expected mass is 2 into 10 power 10 solar mass. So we have got upper limits which are less than the predicted values. And to conclude, this is one of the first KPC scale observation in 1.3 gigahertz for this particular source. And since we are not seeing any extended emission and jet emission at this particular 1.3 gigahertz, and we have also not detected any H1 21 centimeter line. So we cannot conclude whether it's a galactic merger or not, but we think further single observations can help us to probe if due to the galactic merger, if the gas has been emitted to a large extent. So we are trying to look forward in that direction. Thank you. Yes.
Nice work. So you looked for radio continuum.
Yeah.
But do you have enough flux for say VLBA?
VLBA has been performed on this particular galaxy, and but I don't think it's in this H1 emission they have done it, right? It's in higher frequencies, and they see some kind of what is it, extended emission.
So there is on smaller scales there is a radio jet.
I think so. I don't remember it exactly.
The VLBI observation. And I just asked. So In optical, you can't make out whether it's an elliptical galaxy or a disk galaxy.
This is seems to be an elliptical galaxy.
That's why it doesn't have H1.
Yeah.
If not, let's thank Avinash and all the speakers.
Thank you.
Right. What time will start? 2 o'clock.
We'll be back here by 2. So that should be.
Yes, yes. Back here by 2. Thanks, Vika. Nice. I checked the DLBA observations.
Yeah.
The DLBA, like Preeti is an expert.
Yes.
And Ayisha also. You may be seeing that it is just one compact, but on like milliamp seconds might be detected.
Yes, I think there is some explanation which I think is the there is a paper by the Chinese group itself. Done BLBR.
Yes. That will explain.
Yes. And I think I am kind of here in general interested in like to see for the galactic merger signatures because since they are the products of galactic mergers, will there be any galactic merger signatures?
Yeah. You'll probably see moreover, there's had some photometry of the elliptical galaxy or something, shells in the galaxy.
I don't know how to do that, but they say it's the elliptical Seyfert galaxy.
Okay, Seyfert. Yeah, exactly.
So there are currently several projects of the last one binary. So is it check for other galactic merger signatures if any of them coincide with this?
We need to podcast.
It's okay.
Whenever the merger happens, the dynamic will change is large. So actually, shells. But in the inner part, because of the dynamical time, things would have changed fast. You may not see it. You know, the only thing you could is to look for 2 cores in the center.
Okay.
So those 2 cores, they see whenever any merger happens. Black holes are buried inside bulges. Okay, of course, and spheroids or bulges. So you will see them in near infrared.
Okay.
You'll see this stellar distribution.
Yeah.
Compact source.
Okay. But here they are like less than a parsec away because they are kind of merging.
Oh, yeah. Here it's not possible. Yeah, once it becomes binary, actually it becomes very. I guess the binary one of the things is optical variability. Just like you have in that famous one. OJ. So that one you can check for variability. A survey called Catalina or something.
Yes, actually they have used ZTF, which is also the same thing.
Okay.
From that periodicity itself, they have found that it can be a supermassive black hole.
So if you have now a very large sample of candidates, maybe you can go and check for their optical variability.
Okay.
I don't know, maybe people have done it.
Like most of the people, all the candidates that they have found out are from the optical variability. So, yeah. Okay. There is no data available because it requires several decades of data, and there are not many AGN radio surveys.
And what else can you do? I guess you could do X-ray variability, but then again, there might not be that much data.
Yeah.
You could check one thing. You should check if any of them have an FEK alpha line. You can also.
Okay.
If they have if this FEK alpha comes from the inner exchanges. So if there is some variability, that variability will happen in FEK alpha. And always propose for it.
Yes. But another issue is also like the peak alpha line it will take a lot of time to detect it in AG. And they are like very far away.
They are
most
very
of
far
them.
away, yeah. We can take one, Rodriguez et al. 2006, that Dharam showed in the morning, right? So it separated by 6 particles. That is one of the only confirmed Of course, the chapter is not where it comes from.
Yeah.
Because so that's true. They are buried in there. But later on, when like these better telescopes and things like Athena and all, you would think you could tell that okay, we've detected so many SPK lines in the candidate supermassive black hole binaries. Now it would be good to check their variability.
Okay.
And check where, if the resolution is near very low,
Yeah.
it's like that. But if you are candidate, suppose for if they are nearby,
Okay.
check variability candidate. And then discuss it with some
লিঙ্কটা পাঠিয়ে রাখলাম আমি যদি একবার আবার এডিট করি আপডেট হতে থাকবে আমি